Cool. Why don't we get started? I'm Dan. I'm the CTO at Heap. Today we're going to be talking about what Heap is and the problem we're trying to solve and all of the different sorts of trade-offs that go into designing a schema to build this kind of a tool. So just a little bit of background about me. I joined as Heap's first hire 3.5 years ago. Before that, I was a backend engineer at Palantir, where I worked on all sorts of back-endy things and deployability of the product and that kind of stuff. And before that, I was a student at Stanford, where I studied math and computer science and did a bunch of deep learning things. So to start, I'll give you a very brief overview of what Heap is and why our particular take on the problem of analytics makes for such a difficult data problem. And then I'll discuss some of the approaches we've taken towards this over the years and some mistakes. In general, I think choosing your schema is like the most fundamental choice involved in building any kind of product that has a complicated data layer. That determines what reads will be hard, what writes will be hard, what features you can use. Like it's the trade-off that even determines the trade-offs you can make later. So we build a web and iOS analytics tool. The goal of this project is that you can install this on your website or app and then use the data that we collect to answer questions about your users. So that's everything from, do people even use this feature, to how many users come from various different marketing campaigns, to if a user sets a profile picture within their first week, how does that affect the likelihood that 3 months later they're still an active user, or 6 months later, or whatever you want to do. In order to understand how Heap works and why it works the way it works, I'll give you a brief walkthrough of how a traditional approach to this kind of problem and why I think that falls over. So there are a dozen tools for tracking data about users that go to websites and apps and doing basic analyses. They all basically work the same way. Let's say you have some totally hypothetical, non-real hotel booking and home sharing website, and you want to understand some basic thing about it, like how many people are actually booking hotels on this thing. There are about a dozen tools that can help you with this. They all work basically this way, which is you add some event listener on your front end, and you track the booked hotel event whenever someone clicks that button. And maybe you have some other things you want to track, like you have some other parts of your app, and you instrument all these tracking things throughout. Like you might want to track viewing a listing and signing in and entering a credit card and all the things you think are the basic actions that a user will do in your app. So then later, you'll have some kind of question like, what percentage of our users are actually booking a hotel? This is a flow that you would hopefully understand extremely well if you were building this kind of product. So you have all these parts instrumented, and then you can run some conversion funnel, like what percentage of people who sign in later view a listing, and then what percentage of them later book a hotel. So great, we have our answer. Then as soon as you have this answer, you're now going to have a dozen follow-up questions. Like, for example, the drop-off from signing in to viewing a listing is enormous. It's 96% of users don't even make it to a listing. But then of the ones who view a listing, 60% end up booking. So I think a natural next question is, what is happening between sign up and viewing a listing that is making people drop off? Are they actually running a search? Do they get to a search results page? Do they not? Those have huge implications in terms of how you want to build your product. For example, if people are making it to the search results page and not clicking through to the listing, then your search results page probably needs some work. Maybe the call to action isn't there, or maybe the search results are bad, or it could be a number of things. By contrast, if people don't even make it to the search results page, then there's probably some upstream problem. So these kinds of questions, determine, real things real decisions that you should be making. So we want to add some additional step here, like viewing the search page. Now you have to go through this whole loop of getting this logged again. You have to go get someone to write the login code, which is probably their lowest possible priority. And then you have to wait for them to do it and wait for it to ship. And if you're in a mobile context, you have to wait for it to go through the app store and wait for the users to upgrade. And then at the very least, you have to wait some amount of time while that code is live for the event to happen enough times that you have some statistically meaningful thing. So even if you could wave a magic wand and have this code live in production today, you still have to wait for users to do that thing. So I think you're talking about at the minimum 2 weeks for that last step. The other parts of that are like we see everywhere from 2 weeks to months, like depressingly long amounts of time. And then as soon as you have that result, you're going to get like 10 more questions immediately, and you have to go through this whole rigmarole again. Like if you want to go through 2 loops of this iterating on your analysis thing, it's currently November. Let's say each one takes 6 weeks. It's February before you have an actually useful answer to your questions. It's like an insane amount of time. Basically, the point I'm trying to get at is that analytics is a fundamentally iterative process. The iteration speed is the thing that matters the most. If you don't actually have the data, you can't do the analysis that you want to do no matter what. So it's a question of how quickly can you iterate on your analyses. The usual, like other analytics tools will sit down with you and help you build out what's called a tracking plan, which is, you can think of it as like the Soviet 5-year plan of web analytics. You sit down and think through what are all the possible things I will ever want to track on my website. And of course you don't get all of them because it's the unknown unknowns where all the interesting stuff is anyway. But in a fundamental sense, it's an iterative process. You get some results, you immediately have a bunch of other questions you want to follow up and drill down on it and whatever. So the Heap approach to this is to just capture everything that happens on your website or your app and then let you analyze the data retroactively. So in particular, we have a snippet that you include on your website, and this snippet will bring in some JavaScript that we've written that will capture every single user action that happens on your website. So every click, every page view, every form submission, every swipe and tap and whatever. And there's an iOS equivalent that will capture every UI event over there, every swipe and tap and other iOS UI event. So you capture every single plausible thing up front, and then whenever you have some sort of question, we have data going back to as soon as you installed this. So you can iterate on your analyses immediately. So you can when you want to follow up on some sort of funnel, for example, and add a bunch of steps, you already have everything you could want to add there. So this will capture a bunch of raw data for you in terms of clicks. Like what Heap captures when a click happens is like 50 total properties, but something to the effect of a click on this div with this CSS hierarchy happened, and the page view path was blah, and the session referrer was foo, and it's some like raw thing that is not particularly meaningful to humans. So in Heap, we have this concept of defining an event, which is giving a name to a, giving a name, you can think of it as giving a name to a filter. Or, for example, we give you a visual way to do this. So when let's say you want to understand how many people are clicking that sign up button to sign up for your website. We give you this tool where you click this, and then we pull from that we give you this thing where we pull from that, okay, you clicked on a button where the text was sign up, and the CSS hierarchy of that event that you clicked was blah, 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 and you can twiddle it and limit it to various different other options, like limit it to this page or limit it to other parts of this page, or anything like that. And then once you've defined this, we now have this semantic mapping where a sign-up is this, and now you can do your analysis in terms of sign-ups instead of in terms of some raw thing that doesn't make any particularly intuitive sense. Another way to think about this, I think, is instructive, is that the schema is extracted from the data. It's a separate layer. In a traditional web or iOS analytics tool, the schema is embedded all the way into the data. Like when you log so-and-so did a checkout, it's already, like it's fundamentally within the data. Whereas here we have a separate schema mapping layer on top of the raw data that you can iterate on and change, and you already have the raw stuff going back from forever, and you never have to, like that stuff is all immutable. So once you've defined this, we let you do all kinds of things with it. For example, you can build this graph in terms of like button clicks, and you do your basic filtering and grouping. Like you might want to filter likes where the country is Canada, or your grouped graph type stuff, any kind of other basic analysis. This is the basic premise of the product. So this brings up the first really difficult thing about building Heap, is that you're capturing every click or form submission or page view or whatever on a website. All these raw things, the total data volume is enormous. You're talking about 10 times as much or 100 times as much data as a traditional analytics tool will capture. And we can't really throw any of it away because you never know when it will become relevant to an event definition that someone does. So you need to keep all of it on relatively warm storage. But 95% of it will never be of any value. It'll never match any of those definitions. It'll never be of any value. In terms of other things we let you do with this, there's your usual grouped graph type stuff, like maybe you want to do signups per day, grouped by which plan they signed up for. There's your bread and butter conversion funnel type stuff. This is a really core use case for us. You show me the percentage of people who did some action followed by some other action, and then how many made it to some third action, and go an arbitrary number of steps down that. Retention analysis is another important thing that our users care a lot about. For example, for people who signed up in each week of the last 3 months, what percentage of them logged in a week later, or 2 weeks later, or 3 weeks later, or n weeks later? So this is how you might want to analyze churn or the stickiness of your application, that kind of thing. We also have a concept of a segment. So you might want to say, I define an active user to be a person who signed in at least 4 times in the past week, and also either did a friend request or accepted a friend request. So some sort of Boolean has done this, did this at least n times in the last k days, never did blah, some sort of set of rules like that. And then once you have this segment definition, you might want to graph membership in it over time. You might want to use it to inform your other analyses. So you might want to take a conversion funnel and then filter it for users who are in the active users segment, or filter it for people who are not in that sort of thing. What I'm getting here is that the space of analyses we support is really broad. Funnels, retention, all these cohorting features, grouping, filtering. You basically can't pre-aggregate any of the query results because the whole premise of this thing is that it's an iterative process where you can do all kinds of ad hoc queries. So you can't really pre-aggregate the queries. You never know what events you're going to need in a given time, so you can't really throw any stuff away. And in addition to both of these, we care that the data is pretty close to real time. That's a fundamental element we found in people actually trusting it, but also it enables a lot of use cases if this data is within 30 seconds of real time. So that's something that we care a lot about as well. So the combination of these 3 things makes for a reasonably complicated data problem, I claim. Make sense? Cool. So this is your basic data model. There's, at the root of it is a user. Everything is in terms of users. A user has done some number of sessions. A session is a stream of activity in which there is no 30-minute gap. So I guess that is already pretty formal. If you do a bunch of stuff and then you leave for more than 30 minutes and then come back, a new session has started. So every user will have at least 1 session and usually more, or hopefully more. A session is composed of some number of page views. A page view is what you think it is. And then a page view has some number of events. An event is any other thing we capture. So a click, a form submission, anything you manually log, because we still do let you do that, swipes, taps, whatever. So there are a couple observations we can make that are potentially advantageous for us. The first is the data is mostly append-only, although there are a couple cases in which we will want to delete or update stuff that I'll touch on towards the end. But for the most part, this data is write once. You never have to update it. You never have to delete it unless you want to archive really old data or something like that. Secondly, the queries map really nicely to a relational data model. You're doing, if you're doing a lot of filtering and grouping and joining type stuff, like it makes sense as a relational problem. Like if you're doing a conversion funnel from A to B to C, and then you want to filter for users who are in cohort W or in segment W, then that maps pretty cleanly into a join between 2 sub-analyses that we do, and the things compose really nicely that way. The third observation here is that the events have a natural ordering to them. There's a time which is pretty close to monotonic. You can't perfectly control when these events come in, but it's pretty close to monotonic. And all the analyses have some sort of time range component to them. So there's some element, some ingredient what we're doing will likely involve some kind of time indexing or partitioning in terms of time or something like that. And finally, the queries we're doing are in terms of the defined events. So a user's not going to ask for clicks on some random div where the session refer was blah completely out of the blue. It's going to be in terms of one of these event definitions. Those are your repeated units of analysis. So if there's anything that we can pre-aggregate, that seems like the most obvious thing. Like this seems like an important thing to take advantage of. So for the remainder of this talk, I'm just going to walk through a couple different approaches we have taken with this problem. I should also mention up front that our data set is hundreds of terabytes. It's impractically large for a single Postgres instance. There is a whole separate portion of this that's how do you distribute this analysis. For the sake of this discussion, I'm just going to wave my hands and say CitusDB. In practice, there's a bunch more. That's its whole separate conversation. If you're curious, just come grab me after. I'm happy to talk about it. But I'm just going to pretend it's the world is a single Postgres instance. So the first thing we tried, and I claim the first thing anyone should ever try, is your vanilla normal, third normal form, Boyce cod type thing, the thing from your database textbook. So let's say we got a users table, and every user belongs to a customer, and they have their own user ID. There's some bag of properties that people can tag on them, and some that we auto-capture. There's some session table. A user has many sessions. You have a foreign key there. A session has a user and then a session ID and a time and some set of session-level properties. A session will have a bunch of page views. A page view has those same IDs and also a page view ID, and it's also basically the same idea. There's a time and some properties to it, and a foreign key that maps from that back to the session. And then your events live under the page views. So those will be defined by an event ID in addition to the previous ones, and they'll have a time and they have some properties. Like, hooray, the problem is solved. That was really easy. This was great. I think we're all done with everything. So this has some real pros. The first is that it's simple, and I think that counts for a lot. There's not a lot of cognitive load to this. The data model maps directly to the schema, which is always a very favorable thing, because if your data model and your schema don't map very well to each other, you'll have to explain to your users all the time why something that seems like it should work doesn't work, or that kind of thing. And in another sense, like, everything sort of works the way you expect it to. Like, ORMs work out of the box because ORMs expect this kind of data model. Postgres expects this as well. Like, everything sort of natively speaks this kind of schema. Everything just sort of works. There's not a lot of surprises. In particular, it's really easy to ship an MVP, which if you are us then, that matters an enormous amount. And finally, there's one of the traditional benefits of a normalized type schema is that you get the possibility of really great data consistency guarantees. There's not a lot of duplicated data here, so there's not a lot of stuff that can get out of sync. You can slap a primary key on each of those tables. You can put foreign keys between them to enforce the relationships. In practice, for this kind of product, you might not want to, because some percentage of all of those things will get lost. And if you drop a page view object or a session object, you might not want to drop the child events and pages and so on. But in general, you can get excellent data consistency out of this kind of schema. And for these reasons, I think you should basically always start here. And I even put that in bold. Like, this is the idiomatic way to do stuff. Your database is designed with this kind of schema in mind. It's generally going to be really fast. You would be shocked at how long this kind of thing will work. But there are some cons, especially for this kind of tool. For the kinds of analysis we're doing, even a basic sort of query is just way too many joins. Like, those event definitions include parts of the session and parts of the page view and parts of the event, and you might want to filter your stuff in terms of parts of the users. It's very easy to construct an analysis that we'll want to do where you're doing more than 12 joins, and you hit the Gecko optimizer planner, and like you get all kinds of weirdness in that direction. If you want to do any sort of basic analysis, like let's say you want to graph signups per day over the last week, you need to join up a bunch of stuff, and then if you want to filter it for users in some cohort, you're now joining it with some other thing that does itself like 10 different joins, and these are not pathological things. These are basic sorts. This is like the basic pitch of this product, so you should be able to do that kind of analysis. So this fell over pretty badly for large customers. Large at that point in time is, let's say, 100,000 sessions a month, something like that. So not the biggest website in the world either. So there's some space of customers who can use this thing, but a huge range of the market we couldn't support with this kind of schema. So another observation that we can add at this point that we sort of figured out around this time is that the aggregations partition really cleanly at the user level. So if you're doing, let's say, a conversion funnel from A through B through C, it's sufficient to just compute that funnel for every one user, which is going to be like ones for the places they did it and zeros where they didn't, and then just sum them up. And this extends to really all the other analyses that we're doing. Basically, all the aggregations partition really cleanly on the user. So the user, everything partitions on the user. There's too many joins. Let's get rid of all the joins. So this is where attempt number 2 comes from, which is let's just denormalize everything onto the user. Let's something like this. For every user, we'll keep one big array of every event that they have ever done. And when you want to do some sort of analysis, we can scan through that, and you already have this stuff in one place, and you can do all the stuff you need to do. To actually do that analysis, we worked with the Citus team to build some set of UDFs. For example, there's a UDF that takes an array of JSONB blobs and some pattern that defines an event filter and tells me how many of the events match that pattern. Or there's one specific to funnels that just chugs along through an array and sees how far in the funnel you get. Like, find the first instance of event A, okay, find the first instance of event B after that, and so on and so forth. I'll drill down on how that funnel one might work, because I think it's kind of instructive. It takes two arrays. The first is the events, the raw events. The second is the definitions or the filters. Let's say we have these 3 events at the top. There's just some arbitrary JSONB blobs. And we give it these 2 event definitions where the first one is anything where the foo field is equal to ABC. And the second one is any event where the city field ends in and Cisco. This will look through that array, and it'll see that the second event matches. So it'll look for a foo ABC event, and it'll find it in the second event. And then it'll keep going through until it hits the third one, where it sees that matches the second thing in our, our first event in this funnel matches the second raw event, and the second thing in the funnel matches the third raw event. It's a mouthful, but I think it's very clear what I'm talking about. So this user got all the way through the funnel and will emit 2 ones. Whereas let's say I flip those 2 events, I'll look through the array until I hit something that matches that and Cisco event, and I won't find it until the third event. And then after there's nothing left to match. So let's say that this user got to the first thing in the funnel, but not the second one. It will emit a 1, 0. And if the user didn't do either of these, we might emit a 0, 0. So your analysis query is going to look something like this. You'll take that big events array for each user, and you'll pass it into this funnel events UDF along with the definitions of those events that we can just compile in because the users already defined them. And then we'll pipe that all into a big sum, and we get something like the total number of users who made it to step 1, the total number who made it to step 2, so on and so forth. You'll emit something like 110 users made it to the first, 220 made it to the second. And then any query is going to be specific to some particular customer. There are a bunch of pros of this. It actually works reasonably well. It worked reasonably well for us in practice. It was much faster, especially for larger customers or complex analyses. This got us to a viable product. I think this was one of a couple ingredients that made this a saleable thing where we started to get real customers and real traction. You don't pay nearly as much of a sophistication penalty for an analysis, if that makes sense. Like a 7-step funnel is not really going to be any more expensive in this kind of approach than a 2-step funnel. So in that sense, it's a much nicer product to use. So this made it pretty well to customers with on the order of 5 million monthly sessions before it really started to fall over. So if you're keeping track of all those numbers, that's like a 50x improvement or 50x scale increase in the size of customer that we can meaningfully support. So in that sense, this is a pretty large win. You can make these extensions. You can make these UDFs to do reasonably sophisticated analyses like retention type stuff, cohorting things. It's really easy to distribute this kind of schema because there's just one row per user. Every user lives in exactly one place. This was in the reasonably early days of Citus, and it could distribute these without any problems. And one other particular benefit of this is that those event arrays for all but your smallest users are going to be larger than the threshold at which these things get toasted. So those event arrays are going to be compressed, which means on disk they're going to be significantly smaller, and they save you a lot of I/O when you do these reads. So the data compresses extremely well. There's a ton of duplicated stuff in there, like it's JSON blobs. So you get like a 2.5x improvement in your disk footprint from that, which is a pretty significant win as well. But there's some limitations. One is that you can't really index for those event definitions or really anything at all. In Postgres, an array of a variable length type like JSON is not an array of pointers to blobs. It's just a bunch of blobs concatenated in a row. It's sort of like a string that it parses on read. It's a bunch of blobs concatenated together. So not only can you not index for specific event definitions, you can't even index for times or positions in that array. Like if you want to start reading halfway through and then read to the end, you have to read the whole blob from disk, and then you have to decompress the whole thing, and then you have to keep parsing until you get some portion of the way through. Like in a pretty deeply rooted way inside of the Postgres data model, you can't really index for anything. This also means that so when those arrays are going to keep growing and growing and growing and growing over time because users keep doing things, which means your analyses slow down. This is actually really, really bad. When someone buys a product after a 2-month trial and then at month 6 it's like useless and the queries are constantly timing out, like that's really bad for everyone, including us. Like we don't want to like bait and switch people. So this turns out to be a really undesirable attribute of this schema. Another is that there's a limit in Postgres of 1 gig per field value. So like when we were first rolling this out, our largest users were like in the tens of thousands of events, and we were like 1 million events. That's like a crazy number of clicks. Who would ever do that? And it turns out a lot of people do that. A lot of our customers will map one user to actually a customer of theirs if they're a SaaS app, which could mean they have hundreds of actual humans doing stuff. It's very easy to hit that, and you hit that limit, and then there's not a lot you can do to engineer around it, and all kinds of painful things will happen. So we tried some hacks. There were some hacks that bought us some amount of runway. One that we tried was, what if we store for each user a time they were last seen, which is the time on the last array or the last event in that array. So this will let us at least filter out entire users who have not been seen since before the time range of your query. Like we can't index for the subset of the array that's relevant to the query, but we can at least discard a whole bunch of users that we know for sure are not relevant. Another is we pulled out, at the time, around 90% of the queries we were fielding were over a subset of the last week of data. So we thought, why don't we just pull out a subarray here that is the last 1 week of data, and this will guaranteedly contain a superset of the last week, and we can always just trim it and cut stuff. But you should be parsing a much smaller thing, or decompressing a much smaller toast blob. Yeah. No, the question was, is a funnel limited to a session? No, but that's a feature that we would like to add soon. A funnel is over it's over a time range, but it goes cross sessions. We have time-bounded funnels now, but. Oh, I guess we have session. I think we have session now. That was 3 years after this point in time. Only ordered. We would like to add unordered, because a lot of these things, like for different kinds of customers, you can imagine wanting different of those things. There's a million knobs you might want to add to funnels, like filtering for all these different kinds of things. You want it ordered, you want it unordered, you want it bound by time ranges. How do you want to do the bucketing? Do you want to bucket the time ranges by the completion or the former? You want to filter by properties of different parts of the funnel. You want to insist that, like, there's, we're hiring. Anyway, so we tried these two hacks, and if you're me 3 years ago, you'd be like, that's really gross, that's like shameful, what are you doing, that's so hacky. I'm not ashamed. There's nothing wrong with this. These hacks bought us a lot of time. This bought us like 3 months very early in the company. That's a really big deal at that point in time. That's 3 more months to figure out an actually longer-term viable thing. So the way, like an ideal case for these hacks is, let's say we're doing a query that's only over a subset of the last week of data. Then instead of using the events array, we would just use that events last week array. And we can also filter for users who were first, so we have the time range of the query, and we're going to filter for users who were first seen before the end of the query and were last seen after the beginning of the time range. So any user who doesn't match those either stopped being seen before this query was relevant or started being seen after, so we can just completely discard that user. So for something that's sticky, like a SaaS app where your users keep coming back a lot, that events last week array is going to be a lot smaller than the regular events array, so you get some savings there. You don't necessarily get anything out of the other end because most of your users, or a huge percentage of your users, will be relevant to every query. And then on the other end of the spectrum, let's say you have a very bouncy sort of thing where your users don't actually come back very often. The events last week array won't be much smaller than your regular events array because most of your users don't even come back for more than 1 week. But you can filter out a huge chunk of your users because they won't have been relevant in the time range of this query. So, this buys you something. There's another huge problem with this schema that we ended up hitting. How many people here know what MVCC is? Wow, everyone, that's awesome. How many, can anyone guess why this is a very painful schema, given how Postgres works? The exactly correct answer was you have bloat like nobody's business. This is a picture I took of our stack in the middle of the day in fall of 2014. So in Postgres, you're not appending to an array in the sense that you would be in any other sort of context. Whenever you modify anything in Postgres, whenever you update a row, you're rewriting a new version of the row. So if you append one event to a user that's done 5,000 events, you're rewriting now 5,001 events in a completely new row. So, you can see where this would be a problem if you end up finding out later than you expected that you have a lot of users, way more than you expected, that have more than 1 million events. You're doing a quadratic amount of work over time as these users grow. So the right path is a ton of problems. One is that you're rewriting the whole user. You get this ridiculous bloat. You have to turn your auto vacuum knob up to 11. Now you're using all your I/O on auto vacuum. You have more problems from that. Another thing that is really painful from this is that like very simple maintenance starts to become really complicated. Like keeping those arrays sorted in terms of time, which is a precondition for a lot of the UDFs to work efficiently, that turns out to be a lot. Whenever you add an event to this user, you now have to sort this like increasingly long array. So you get a lot of pain on the right path here. Just to give you one particular like order of magnitude anecdote, we measured that the total volume of the write-ahead log over 1 week was about 100 times the size of the database. So your full size of your total like longitudinal data set is 1% compared to the amount of rewriting that you're doing in just 1 week. So pros and cons. This is a picture of our database bloating out of control during 1 week, and then you vacuum everything Friday night. This is a 3.2 terabyte machine. That's 500 gigs of bloat happening in the span of like 8 hours. It's painful. So we'd like to do better. Another observation that we can make that we at this point we have a lot more users and a lot more data on how they do stuff. We can amend this previous observation to note that not only these analyses always in terms of those defined events are really sparse. the percentage, you can think of it as the percentage of your clicks on your website that are on the checkout button is really, really small. That's 1/10 of a percent, 100th of a percent, some really small subset of your data. So those are really sparse. We want to organize our analysis around that. Like, how do we optimize for an ability to pre-aggregate or index for these event definitions in particular? So those event definitions can be in terms of the session or the page view or the user. And we'd like to be able to do some kind of indexing at that layer. So this is sort of where this third attempt comes from, which is why don't we denormalize the events together but keep them split out separately from the users? So you'd have one users table where there's a customer ID and a user ID and some properties and a primary key on it. And you'd have some event table where there's a foreign key back to the user table, and every event has a customer and a user and a time that it happened, and a data blob where that session and page view data is replicated. So every event from the same session will have the same session stuff written multiple times. And then to actually make the analyses efficient, we use this sort of trick where Postgres has this feature called a partial index, which you can think of as an index with a predicate. So it's like an index with a where clause, where this index will contain exactly the rows in your table that match that predicate. So any event definition that you do, because all of the properties of the event are denormalized in, any event definition you do maps to some predicate on the rows in that table. So in particular, let's say you have some definition where an order confirm is a click where the page view path is /checkout, and the text of the thing you click is confirm order, and the CSS hierarchy matches some glob pattern, something like that. So we maintain under the hood for every event definition you have one partial index that corresponds to it. This turns out to be considerably cheaper than it seems because those events are so sparse. So on write, you're checking all of these predicates, but you're only writing the ones that match. And since 95% of your events don't match any of these ever, 95% of them don't end up impacting this at all in terms of I/O. And then when you're evaluating some kind of query, the planner is really smart about using that predicate. So let's say we're graphing confirmed orders per day over the last week or something like that. Postgres, the planner is smart enough to realize that the predicate on that where clause on the bottom query implies the predicate on this index. So any row I could possibly want here must be in that index. So we can just scan that to get exactly the rows we want. So you can think of this as like a whitelist to exactly the rows that we care about that are relevant to this event definition. And all the queries are in terms of those event definitions. So you get you can get pretty great performance even if your query touches 10 different event definitions, like a funnel across 7 steps, and then you have 3 other filters related to some other events. You're still just doing 10 scans on these partial indexes that are going to be really, really sparse. And because that index is on time, you can get the time range of these things really quickly, like all the instances of this that happen in a really small time range. So basically, the strategy is that we maintain one of those for every single predicate for all of those event definitions. The variety of things we capture is so enormous that all those individual definitions are really selective. And this degrades really nicely given our retroactive analysis framework. Like we're never modifying the raw events. The raw events are always there. And we create this index as soon as we can. And at least in terms of correctness, it's best effort. If the index is missing, Postgres just won't use it. As soon as it starts existing, Postgres will start using it sort of for free. Like Postgres manages a lot of this stuff for us. We don't have to worry about it. In that sense, it works really nicely. And then you can do sort of any of these kinds of analyses that you want to do because they all shard cleanly by the customer and the user. And then you can use these same UDFs that you had from before and just build up a dynamic array of only the events that you care about. So instead of all of a user's events going into this funnel events UDF, for example, you can just dynamically create an array of all the instances of event A, B, and C, where your funnel is from A to C, and then you pass it in, you get the same result. And then you can join arbitrarily for more filtering or grouping or whatever, but If the core number of event reads you're doing is really small, like all the joins and stuff you do later are not going to be nearly as painful. So it works in a basic sense. We had generally massively better read perf, like for the 98% of queries that match the assumptions that I listed. And I'll get into the edge cases in a moment. It's much, much more flexible in the sense that when you have new analyses, it's usually pretty easy to make them fast. This is currently supporting customers doing on the order of 30 million sessions a month. So that's a factor of 6 over the 5 million I listed previously. That's really understates the gain here. We are supporting 30 million session a month customers massively better than we ever really supported 5 million session a month customers before. Like this product works in a fundamental sense for even our largest customer right now, which is really cool. We spend almost no write time on, like we have surplus IO on write, which is really cool. And on the reads are still bounded by IO, but we're doing a really tiny, like generally we're doing a pretty small amount of it, so they're still pretty fast. And as I mentioned previously, all of the complexity around, or a lot of the complexity around maintaining these things under the hood, Postgres kind of deals with us for free. So that's pretty neat. There are some limitations. One is that it's really expensive to maintain all those indexes. Our largest customers will have on the order of 1,500 to 2,000 event definitions. So in terms of the query planner, it generally holds up pretty well, but that's a lot of predicates, and most of them have some kind of like expression. So you're doing 1,000 like expression evaluations for every event that comes in. That's like a pretty huge amount of CPU costs. Another is that these events are living in JSON blobs, and Postgres doesn't really have statistics stuff for JSON blobs yet. So there's not really anything meaningful for the query planner to go off of. So in particular, the query planner is going to massively underestimate, for our queries at least, is going to massively underestimate how many rows will be returned by each of the sub scans. So we might be pulling 100,000, which is a pretty small amount, but it'll think that only one is going to come back. So it's really easy to get joins that are explosively slow because Postgres thinks that there's only going to be one of something when there's actually 100,000. We found no real workarounds for this. Like we had to globally disable nested loop joins, which I think is usually a massive no-no, but we found no other way to keep them from happening and stuff blowing up. And also another drawback here is that some of the assumptions I listed are sort of restrictive. Like you might have event definitions that are not very selective. It's totally plausible that you get that. And you would like to be able to do some amount of ad hoc querying without an event definition. So you might want to do a really quick, just like show me the page views that match this path per day. I don't need to actually define that and have it exist in perpetuity. Like I just have some one-off query, and that'll be generally pretty slow because it's not very indexed. Like there's no partial index for it. So I will amend this observation yet another time. So another thing we noticed around this time was that so you can technically define a pretty close to arbitrary predicate on these raw events, but they're not totally at random. Like they generally follow some amount of patterns. So if you take the 6 or 7 fields that exist most commonly in these, about 2/3 of the indexes use a subset of only those 6 or 7 fields. So another way of putting it is like if we didn't have to create partial indexes for events that were a subset of those fields, like that would save 2/3 of them or something like that. So that brings up the attempt number 4. Keep the same mostly denormalized events, but extract the common fields out and index a small subset of them that is actually commonly used in these definitions. So here was your event table before where there was a customer, an event ID, and a time, and a data blob. Let's pull out the commonly occurring fields, like the type, the hierarchy of the click, the target text. There's 45 of these, so you're adding 45 columns to your table. We can do we can do everything basically the same as before, except these things aren't in the data blob. So one benefit off the bat is that the data set's about 30% smaller on disk, which is huge because you're not writing those key names everywhere. We actually found that 2% of our data set on disk was the words session ID and page view ID repeated because it was in every JSON blob for every single event. So a huge amount of, like 30% across a multi-100 terabyte data set is like a pretty tidy win. Secondly, the query planner for those 45 columns, which are most of the data but not all of it, the query planner has much more information to work with because those are now vanilla columns. Those are text or ints or something like that. So we can lean on the planner to do more ambitious things. So in particular, you can somewhat reliably get bitmap joins out of indexes on individual columns, and you can make use of multiple indexes within the same query. So once we've pulled this stuff out into columns, we can create direct indexes on the really small subset that make up 2/3 of our event definitions, which is the type and the hierarchy and 5 other ones. And the planner now has enough statistics to meaningfully use a bunch of different, like we can reliably get bitmap joins is really what I'm saying in way too many words. Like we can do much more ambitious stuff that way. So we can replace about 60% of those partial indexes I mentioned with a really small set of simpler indexes, which is really nice. So there's some amount of trade-off there, and you have to pick which ones you want with some amount of profiling. But in general, you save around half the CPU on write, which is our biggest cost bottleneck right now, is like the enormous amount of CPU that goes to evaluating all those like expressions. You have to spend about 50% more on write because you have to maintain these full table indexes for 7 or 6 different columns, which is a lot more than even hundreds of those partial indexes because those partial indexes are so sparse. Another really nice feature of this is that it eliminates a whole bunch of edge cases to our querying. Like if you have a non-selective event definition, we can just not index it. And most of those are in terms of those built-in things, like, for example, page views with a certain path. That's sort of natively covered by this. Like these core indexes kind of give you that one for free. So you eliminate a bunch of these edge cases, and it generally degrades a lot more gracefully. So yeah, in that sense, it's a much nicer life. There's another interesting question to this that I'll leave you as more of a take-home thought that is like yet another problem that I think looks really simple on its face, but actually turns out there's a million different ways to represent this, and they all have big implications on how your stuff works. We support an API where you can tag a user with an identity, and if 2 users have the same identity, we should merge them together. So this is how you might want to do cross-device tracking. If you log in on your phone, and then you later log in on your website, we give you an API where you can send the username, and that should look like one user to you. When you do a conversion funnel across the 2, you should be able to do that. So how you actually want to represent these user moves is quite interesting. You could keep a big mapping of what users map to what identities, and then you could resolve it on read. That turns out to be not viable given our distribution strategy, and then I think even if it were viable, I think you wouldn't want it. I think it would be much slower on read. You could move the events to the new user directly. You could move the events to the new user and leave a pointer behind on the old user that you now belong to the new user. So if stuff comes in out of order, you can resolve that sanely. These have all kinds of different trade-offs in terms of what inconsistencies are possible, which ones will be visible to your user, what reads will be fast, what writes will be fast, how much does this move operation cost. I'll leave it for you, but it turns out there are a whole bunch of different ways to do even something simple like this. This is also a way in which our data is not actually like insert only, never update or delete, because you might actually want to modify the user that an event went to. So there's a whole bunch of other things we might want to do at the schema level, like partitioning that events table. There's a ton of things we could do there. Partitioning it by time, because these things have clear time ranges. Partitioning this by high-level attributes of the event, like whether it's a session or a page view, or partitioning it by the page view path that it's on, or any kind of thing like that. There's all kinds of work we're going to need to do to extend this to support a much more heterogeneous data set. So a big focus for us right now is integrating additional third-party data sources. So you have data about your users in a million different places. You have payment events in Stripe, and you have A/B test variants in Optimizely, and you have email marketing things where you sent them an email in 4 different tools. And we should just pull in all of that and automatically route it to the same user, and like that enables all kinds of analyses that you otherwise couldn't do. That's kind of the whole Heap pitch, is that if you don't have the complete data set, like no amount of analysis power is going to save you. But mapping that into this schema is actually very interesting. Like it follows all of these approaches are how to deal with one massive data set that has a bunch of small defined events in it, whereas this is a lot of those, but they're sort of differently shaped, and you kind of know what they are ahead of time. And then there's new analysis paradigms that we'd like to support. Like we'd like to support things that just don't map into this way of thinking, like flows of users over time, where you don't actually have defined events relevant to this at all. And there's a bunch of other stuff. Come talk to me after if you're interested. We're very hiring. There's a lot of things we'd like to be doing in this area. I have to give a quick plug for my Postgres wishlist. It is long. It includes many other things. Come talk to me after if you want to talk about that. But in brief, the top of mind things for me right now are, as you can imagine, some way to move table data that moves the indexes with it, so you don't have to rebuild the indexes whenever you move some shard of data. You can imagine for us that's an enormously expensive thing. If you have to recreate 1,000 indexes for 2 years of data for an enormous customer every time you want to move their stuff around a distributed system. There's all kinds of gotchas on partial indexes and composite types if you want to get index-only scans. Similarly, keeping the visibility map up to date for a data set where there's not a whole lot of deletes or updates is really hard, unless you're like constantly manually vacuuming, and that has its own costs. So some sort of way to keep that up to date more easily would be enormously valuable for us. And additionally, there are all kinds of distributed systems features that seem like they're sort of down, like in the pipe, but far-ish away, like the ability to replicate single tables so that we can do shard level replication in a simpler way, that kind of stuff. There's a lot of stuff that would be really valuable for us around there. Some of that stuff that Citus is also building, which is pretty neat. Cool. I have, I think, 2 minutes for any questions. Go for it.
How often do the clients create new events, and how do you deal with this creation of data so you actually scan for data for that?
The question was, how often do clients create one of these event definitions, and what do you do? Typically, they'll do it in bursts, like they'll log into that event definition, that event visualizer, and click, define 4 or 5 different things. And the answer is yes, we do a one-time pass to get all the instances of it, and then like create the index from that. Another thing on this wish list, by the way, is it's not there, but a thing that on my mental wish list is some way to create partial indexes based on other partial indexes or based on other like existing indexes. Like if I'm looking for a really narrow predicate, the actual like correct SPI call for that is a much smaller, like it would use other indexes to get the rows. So as a person who has never written a patch for Postgres before, it seems like it should be easy. But yeah.
Does it mean essentially that the client itself will conquer its own performance, but if you want to advance?
I didn't quite parse that.
So the client would essentially conquer performance for itself by creating events.
Yeah, I mean, in some sense, you are giving the client a lot of power. I mean, we throttle these things. It's pretty. It hasn't been nearly as much as a problem as you might expect. And if the indexes are missing, it's not the end of the world in most cases, because you still have some base indexes to fall back on, and for non-enormous customers, you can generally survive. Yeah.
So reading between the lines, you're spawning indexes all the time in response to user actions. How do you operationalize that?
That's an excellent question. The question was, how do you deal with this? You're creating tons of indexes all the time in response to user stuff. We have some set of services that keep track of, like these things go into a queue. They're pretty heavily throttled. We can not. It's not that difficult for us to bound the number of these that are happening at any given time, like the amount of I/O or CPU that's going to them. Like in terms of operationalizing this, a much more common problem for us The problem of your users can DOS you by doing this stuff hasn't actually come up nearly as much as you might have expected. Even for large customers, that hasn't been that much of a deal. A much bigger one is when you do distributed systems operations, like moving these things around, it is very easy for that index creation part to be like a 100x bottleneck, and that turns out to be extremely painful for us.
You've got some kind of asynchronous infrastructure that's running create index concurrently commands, and you're limiting the number that can be concurrently available.
Oh, I'm glad you brought that up. So we actually can't use create index concurrently because you can't use create index concurrently. So multiple concurrent index creations in the same table will serialize under the hood.
Right.
And also they're like 3x slower. And also they will wait on any long transaction on the database wide. So a single long transaction will make your create index concurrently calls hang. So we actually do regular create index, and then we have like the rest of the system deals. Like the writes will all fast fail, and they'll go into some other place where we try them again later. And but yeah, of course. I mean, eventual consistency is your friend, I think.
I wanted to know what's left in the JSON blob after you pulled out 4 UI.
Oh, that's a good question. So the question was, what's left in that JSON blob after you've pulled out all these things? So there are a bunch of ways where customers can submit custom properties. I think there are some not widely used built-in things that we capture. They're widely used. They're so not widely used that we just leave them in this blob. There's generally not that much. It's more of a catch-all than a core thing. Go for it.
Yeah, if you guys ever reach the limit on the number of index on a single table, or if you know if there is a limit.
The question was if you ever hit the indexes per table limit. I think it's 16K. I'm not actually sure what it is. We've never hit this or gone close to it. If we get that many, we would probably do some, like you can be smarter than we are here. Like you don't need to necessarily have all of them. You can keep track of how often these event definitions are used and things like that, and degrade gracefully in that regard. Like it turns into an optimization problem. I think you can have at least 10x over where we are right now. Go ahead, Josh.
So one of the features added to 9.5 was some substantial improvements in cross-column statistics. For some of your pre problems, did you test any of that out?
The question was 9.5 had a bunch of cross-column stats improvements. The profiling we did on that stuff was on 9.5, I think. Is that correct? Yeah. We didn't compare 9.4 and 9.5 though. I think we just checked on 9.5. We should.
The main problem is that JSON doesn't have statistics at all.
Right.
So yeah, so like you make cross columns, but
Yeah, well,
it's not going to help you with that.
yes. Now, the way to be is always going to assume a flat selectivity.
Right.
You just need to go ahead and pay somebody for a year and a half of work to figure out how to put statistics on JSON heap. Not only will not figure out for Postgres, but not for anyone in the industry.
That's a thing we'd pay for. Like, it's a core thing for us. I think I've, go for it.
So how you actually generate the smart ID and the user ID? Because I see that you actually use the instead of using the UID. Like, is there any source behind that?
Yeah, the question was where does the user ID come from those users? It's just a random client-generated UUID. We actually care a lot that that's on the client and not on the server because you want to be able to just start sending data without getting a response from us. Like if we go down, we shouldn't drop data as a result. We should be able to store it in like ELB logs or Nginx logs or something like that. I think I might have time for one more. Go for it. I think I understand what you're asking. You're asking like how viable would it be? I think I understand. Are you asking how viable would it be to keep a separate table for each of those defined events and then have some period of unavailability after you define one where we, yeah, this is a thing we played with at one point. I think it would be, So given how much, like it is definitely nice to have a thing where in some kind of operational stress, we can not create those indexes for even a day, and it's kind of okay. I think we're pretty sensitive to that flow around ability to use those event definitions as soon as you make them, because like that's the fundamental iterativity of the analysis. So my hunch is that we would be pretty unexcited about there being some kind of gap there. But there's other benefits of that, like not creating, like we could do the event def evaluation on write and then not have to have Postgres worry about it. It's a thing to play with. There's like 8 other like similar weird ways to do it. I think I'm out of time, but there's nothing, it's just lunch now, so I'm down to just answer as many questions. Yeah, well, I'll be here. Why don't you?
Actually, I should try to ask, I'm not trying to, you said you are Schema with the first design. So you have the 3 designs, and why can't you the last design from the very beginning?
Oh, that's a great question. I'll give people a chance to mosey. So the question was, why did you do the first 2 designs? Like the third one seems a lot better. Like why not just do that from the beginning? That's like a really good question. There are some portion of this, being honest, is we didn't know better and we learned a lot of stuff along the way about our users and about Postgres. Another portion of it is the distribution story. Like we used Citus for the read path, and it was only reasonably recently that they could support the kinds of joins and subqueries and stuff that you need to do that kind of schema. Another portion is we were like learning the whole time about our users and stuff. I think it's fair of me to say this is a pretty weird approach to this problem. Like there's not an off-the-shelf thing I've seen anywhere before. So it definitely did take us some amount of time to just like have that idea and play with it and stuff. And iterating on these things is something that takes a lot of time. Like iterating on the fundamental schema of this thing. Like you can profile a bunch of them in a day, but it's really hard to do profiling that you can trust. And we've had a lot of other headaches with that. And yeah, I think that was a good enough non-answer here.
Yeah, I think the assumption will change, right? As we realize there's so many learning.
Yeah, so I tried to hide it in those observations. Like some of those are just things that took us time to realize. Like it was a surprising amount of time before we realized that indexing for those event defs is the key to making this product work. Like that's the reason I think you can't use HBase to build this product. That you can't index for the event, as far as I know, you can't index for the event defs and also make it possible to do all the queries that we want to do. So that combination is what makes it worth bolting a distributed system on top of a natively non-distributed thing like this, which is a ton of work on our end as well. I think that's, oh, you have one more?
So how you resolve schema migration?
The question was, how do you do schema migrations? Is a big project every time. Like, it's this in a distributed context, and I mean, everything's eventually consistent, so it usually boils down to something to the effect of, you know, we have our current schema, we have our new schema, we do some background copy, we do some playback to catch it up to real time. At this point, we start writing to both, and they're both live. Then you can start reading from either. It usually looks something like that, because we've structured all of our writes to be idempotent and commutative. But it's a for reals project every time.
So do you use any third-party tools, or it's just
No third-party tools. We'll probably, if we do the partitioning, we'll probably use Pathman or something like that. Pathman looks like a super cool piece of technology. But for most of the other stuff, I think we just do it ourselves. Yeah? The question was what sort of multi-tenancy scheme do we use? So this, let me back up to the, yeah. So this event table and the user table are sharded first by the customer and then by the user. And they're sharded with the same boundaries, and then shards that correspond with the same range are physically co-located. And Citus is smart enough to realize that you can, if you run some query that's restricted to some customer, then it'll figure out only the small subset of your shards that matter, that are relevant to this, because they're sharded first by customer, and it knows the metadata. And it's also smart enough to realize when all your underlying shards are physically co-located, that you can just turn your join into assuming it's legal in your query, which it always is for us, you can turn your join into a series of small local joins and then reassemble the results because they're all AGs. So I guess like the TLDR answer for that is many logical shards spread across a bunch of physical nodes, and then Citus deals with most of the read path complexity there.
It's not separate tables per user, it's just the Citus shards, the separate tables, but not some other, not schema level separate tables.
Correct, it's one big event table. I took this from our code, except I cut some stuff out and then simplified it. Yeah.
Good question. You said shard by customer ID, then user ID.
Correct.
How does that mechanism work in Citus? Unless you have a composite key component using that.
We do need to use a composite type, which is the source of some other headaches because the partitioning logic is not extremely good on composite types, and Citus is just using the partitioning logic. Yeah, something to, like it can't make inferences that you would imagine it should work. Like there's a composite type for customer ID and user ID, and if I have a where composite dot customer ID is foo, it won't realize it won't realize that that's equivalent to, or that implies the range is between here and here. And then but then on the other end, you have issues where it won't use indexes are a lot more efficient if you do them on the composite, on the underlying pieces instead of the full composite, and joins are the same way. So this is a source of some amount of headaches for us.
Distribution though is not, this set of tables has a single customer with their IDs.
It is, so so basically the invariant that we keep is for any, either a customer's data will all be on one shard and we'll lump a bunch of small customers there, or a customer's data will be across many shards and it will be the only customer on all of those shards. So it's range, not hash. Correct, yes, oh yeah. So you're actually doing a small number of subqueries. Oh, really? Oh, apparently range partitioning is a secret part of Citus.
It's because it's so nasty to maintain.
In terms of, hard to maintain in terms of,
You have to really know what you're doing.
hard to maintain as us.
Yeah.
Oh, we know what we're doing.
The user has to maintain it manually because it's so complicated.
Yeah, so we do all the,
Unbalanced. Because you're doing range partitioning and then the number of items attached to it.
But even that, just think of all the different possibilities for the ranges.
yeah. So we have a fair amount of logic to deal with that. Like,
Just range, that explains it.
a customer will grow faster than other customers, and you need to split them up into fewer stuff. That's why you have to subshard by user and that kind of stuff. So whenever you want to do that, you need to recreate a bunch of new places, and now you need to recreate all these indexes because we can't move them. So that turns out to some amount of pain. I think that's all the questions. We're good.